Hi, everyone. Thanks for joining this session. Let's get started. So today I'm going to introduce Gen AI, talk about the landscape, tools, and learning path altogether. We will be talking about AI automation, computer vision, large language modeling, some of the related applications. We'll talk about LLM ops and AI operations as well. And in the end, I will introduce, some of the courses WeCloudData has related to generative AI. So let's talk about AI automation first. I think that's the first step towards, generative AI, and it applies to pretty much everyone. So what is generative AI? Generative AI is part of deep learning. So if you look at, you must have heard about machine learning, deep learning, LLM, generative AI, but also AI in general. Artificial intelligence is more high level related to applications, right? If we're talking about robotics, autonomous driving, they apply AI technologies, but it's not only AI, right? AI is used as part of the ecosystem. And machine learning is part of AI. And it's usually associated to, automating tasks using mathematical or machine learning algorithms, right? And there are different types of algorithms. And the goal is to help us to scale and automate things using these algorithms. And of course, you can use machine learning for many different tasks. We'll talk about that briefly. And deep learning is in particular, related to neural networks, which is actually one type of machine learning algorithms, and it focuses on deep neural networks, and it happens to perform really, really well on some tasks, certain tasks such as natural language processing, LLMs, as well as computer vision. And generative AI is part of deep learning. I think it's powered by deep neural networks. Most of the Gen AI applications using deep neural networks, and it focuses specifically on the generative, models and generative tasks. Anything related to generating images, videos, generating text, audio. So those are generative models. LLM is part of Gen AI, which focuses more on generating text. But since the beginning of LLM or the GPT-2 algorithm, LLMs has been applied to many different tasks such as summarization, text classification, image captioning, right? But now you have video to text, text to video. So there are all kinds of applications. Okay. But generative AI is such a big, broad topic. And we hear things and we see different things, and we may understand that differently. I think for most of us, whether you work in finance, you work in healthcare, or you work as a data scientist or a data engineer in the data field, I think Gen AI is a very useful tool to help boost our productivity at work. So I think we all have some sort of experience with Google Gemini or ChatGPT, right? This kind of product, and then we learn how to use prompt to ask questions, to do Q&As, and do different kind of automation tasks. This is what Gen AI can help. It can help us become more efficient, right? And it can also help us with the machine learning tasks. For example, you can use Gen AI or large language models to label the data and then train more specific models. And then, of course, a lot of companies are trying to use Gen AI tools to build data science products, chatbot and things like that. Most of the time, I think we're all users of Gen AI technologies. So we need to learn how prompt engineering works. But I think some of us will end up building Gen AI applications or even, large language models. So that is more, technical. So I think if you would like to go down that path, you need to learn how to pre-train LLMs or fine-tune models, And I guess practically speaking, I think most of us may actually be involved in some sort of building RAG LLM powered applications. Because I think at this moment, um, we all acknowledge that like pre-training a large language model from scratch, it's actually not that hard. The tricky part is, how to scale the data collection, data cleaning, and also you need to have the computing power and also the budget, right? The money to train these large language models from scratch. So it's either open sourced, right? We're going to be working with open source large language models, um, open sourced at Meta or by some other communities, or just go with the Open AI model, which is not open source, right? Those are closed source LLMs. So yeah, that's a quick intro. Now let's dive a little bit deeper to understand Gen AI, machine learning, deep learning. Okay, so you can think of Gen AI as this, black box, and it does some sort of magic, but it follows very similar pattern when you compare that to the traditional machine learning, right? It expects some sort of input and it gives you the output. Um, in conversational AI, we know that we need to sort of, give the prompt, right? The prompt can be text prompt, it can be, voice prompt, and then we're sort of expecting the output to be text, image, or video as well. So you can apply this to, in text to text type of applications, but it can do text to video, text to image. It can do, image to text and image to image as well. But on the output side, after receiving the text prompt, the Gen AI algorithms will generate some sort of images, and that's the generative part, right? So what is LLM? We explained that Gen AI expect input and gives you output, and it's not necessarily limited to text. It can be, any type of unstructured data, right? It can be 3D data as well. So what is large language model? Large language model, some people say that it's the next token predictor. So the reason why ChatGPT can, spit out words, right, and also makes a lot of sense is because it has been trained on massive amounts of, text data. And it does something called autoregressive models, which essentially predicts the next word. But when you're training these models, you basically have to feed the text into a transformer model, word by word as well. So it goes through many steps. Here, for example, the first step is the input, right? Is my name is, and the output in the training data can be ChatGPT. So imagine you scrape this data from the web. Someone is saying that my name is ChatGPT. And then you can construct the input and output, right? So ChatGPT can be the output, and my name is the input, and you feed that into the LLM, and this is basically one record, right? But it keeps going. Step 2, my name is ChatGPT, now becomes the context. So the context is the input here, and the output will be the comma. So basically, you take a paragraph of text, you tokenize it, and we're going to construct this kind of training data where it always, use the next word as the output, right? And then it continues to learn from that. And after it has seen, a lot of text, and it starts to mimic, human, and starts to talk like a human. That's essentially, in how LLM works, and that's why it needs to see a lot of text data. The training cost is very high. Okay, this is called autoregressive model, and it essentially predicts the next word. But of course, the next word, right? This is the training process. We have to feed a lot of text into the algorithm, and then it knows how to predict the next word. But the next word, there are many different options, right? So here's one example. The Toronto Raptors won the 2029. Let's say that's the input. We would like to feed that into a a pre-trained large language model. And this model is going to be able to predict the next word, but it has many options, right? Imagine the token here is just a word, right? To simplify that. So it can be Toronto Raptors won the 2029 NBA. It won the 2019 basketball, football, right? And then the next token, each one of these tokens has an associated probability. And then there are different ways to choose the next token. But let's say in here we choose the one that has the highest probability, then it's going to be choosing NBA. So it becomes the Toronto Raptors won the 2019 NBA, but it needs to do the completion, right? So it will keep predicting the next token or next word. So now it's going to use that, the word that's predicted previously, which is the NBA, along with the previous context. And now they are the new input, and you feed that into LLM again, it's going to generate the next output. So predict the next token and select the one that has the highest probability. So that's how a generative model choose the next word, and it does some sort of completion. And that's essentially how ChatGPT works. It significantly oversimplifies this, but that's what a next token predictor works. Okay, and most of the LLMs are decoder-only models, which means these are the generative models we're talking about. Okay, so that's LLM. And what can we do with these LLM? I'll explain a little bit more about LLMs, the life cycles, and how we can use it. But here we're still just talking about using Gen AI for different tasks. And the most useful use case of Gen AI right now, I think, is using that as part of the AI automation workflow. Right? We can use no-code tools such as Power Automate by Microsoft, or Zapier, or even use no-code machine learning tools such as SageMaker, Nime, RabbitMiner. They all integrate with large language models now, and they can use that to do different things. In machine learning, you can use LLM to generate labels for you, right? If you want to train some sort of classification models, right, you can use LLMs to, let's say we would like to build a sentiment analysis or sentiment classification model, and you don't have the data labeled. Traditionally, we can manually label the data, or we use human annotator, and you have to pay for the service. But now we can pay an LLM such as OpenAI GPT-4, use that to label your data. And then you can train your domain-specific, sentiment classification model. That's one use case of AI automation, right? But you can use that to build other workflows. Using Zapier, for example, it has integration with thousands of SaaS tools. If you would like to automate, the reading and reading and replying emails based on certain criteria, you can do that using Zapier and ChatGPT or OpenAI models, right? So it can automatically connect to your emails, connects to your calendar, and it can you can feed the email text as context into OpenAI, and then it, depending on the tasks, whether you want to summarize the email, extract some key information, or generate response, and then Zapier can help you automate the email response, or it does some sort of filtering and then notify you through Slack or text message. But this kind of automation, workflow automation, can help you save a lot of time and help your startup or your team become super efficient. So that's what these tools can be used for. I highly recommend. This is not that technical. It's all about just working with some no-code tools, and also understand how to do prompt engineering and work with OpenAI or equivalent models like Google Gemini models or Anthropic Claude 3, and then you can automate a lot of things. There's some other use cases, right? You can use that Gen AI tools for transcribing videos, and when the transcription is done, it can summarize it, extract key information, and then send a notification, or you can, save the transcription somewhere in a database, in a Google Sheet, wherever you want to be, right? You can do email automation, send reminders, use it to update social media, posts, do some basic data analysis, right? Generating to-do list, you name it. There are a lot of interesting use cases. Okay, so how do we get started with generative AI and prompt engineering or AI automation? I think the first thing you need to learn is just how to do prompting. Some people say that prompting will go away when the Gen AI models become more and more powerful. But I think it's always going to be useful, even though the new Gemini 1.5 Pro models now supports like millions of tokens or context length. But still, like, if you know exactly what you're expecting, create a better prompt that will make your large language models or whatever Gen AI tools life easier, and it will be able to give you better responses for sure. So you need to craft your skills on prompt engineering to learn how to work with ChatGPT, and use that on a regular basis. And it's super powerful. It doesn't do everything you want, but if you want to do brainstorming, ideation, right, you would like to do some sort of summarization, and this is what it's really good at. So learn the basic prompt engineering, prompt design. That's the first step. And then work on automation. We all have things that we can automate. We always wanted to automate. And now with tools like OpenAI and Zapier, I think we can build automation workflow, and hopefully we can double or 5x our productivity and even become a more efficient data analyst or data scientist. The next level will be applying Gen AI for data science and machine learning. It can be used as a tool to enrich your model, help you automate data annotation. There are a lot of great use cases of Gen AI in data science and data engineering as well. I know there's some companies that are trying to do text to SQL, but basically even sort of automate automatically generating SQL queries. It doesn't necessarily remove the need for data scientists and data analysts, but it's going to help you become more efficient for sure. We've also seen tools like Devon, which sort of try to automate software engineering. It's only at 14% right now, so definitely we don't need to worry about being replaced as a software engineer. I've sort of been paying close attention to the trend and reading Reddits and different articles. And I can tell you that serious engineers wouldn't believe that they will be replaced that soon. So I'm not really worried. I think we all just need to upskill, keep upskilling ourselves and stay very close to this trend. Then I think we'll be doing fine. But if you would like to move onto the more technical spectrum of Gen AI, I think you need to seriously build your ML and AI fundamental skills, meaning that you need to understand how machine learning works, and then deep neural network. Also work with tools such as TensorFlow or PyTorch, right? If you want to work with large language models, then Hugging Face will be very useful. You need to understand the fundamentals of transformers, which so far is still the best method for you to train LLMs at scale, right? But there are some new innovations out there, which I mean, transformers is definitely not going to be there in a few years. There must be new frameworks and architecture that can help us to scale this even further. There's some already some very promising frameworks out there, architectures out there. Okay. And after that, I think fine-tuning large language model is probably a more pragmatic approach, right? Building RAG. This is the most popular things that's happening in the enterprise world right now, because not every company is interested in training their own large language models, but they very much want to fine-tune a model and tailor that to their own specific, proprietary data or use cases. and they're not comfortable uploading their private data to OpenAI. Or if they would like to bring OpenAI in-house, the cost will be very, very high. So fine-tuning becomes a more practical, approach. But there's also another approach which is called retrieval augmented generation, which is also very popular in the industry. They both have pros and cons, but some people use them, combine both of these for their own use cases. Okay, so that's how we get started. My recommendation: just start, learning prompting, work on AI automation, and then you need to start learning more about data science, machine learning fundamentals before you move on to large language model modeling. There's some available resources. WeCloudData has a Gen AI introduction course. It's now a self-paced course. And then we also have specialization courses, which is the LLM engineering course. There's some great online resources. You can go to deeplearning.ai. They have, I think, a lot of very good Gen AI courses. I think it's owned by Andrew N. So they have LLM courses. They have NLP, many, a huge collection of short courses. Most of those courses like 1 or 2 hours. So it's very introductory level. So if you want to go deeper and do more exercises and work on projects, you can consider, watching some YouTube videos. I see like there's some great resources on YouTube. Coursera has some, large language models courses as well. Databricks, which I think a couple of weeks ago just released one of the best open source large language models. So they have a free LLM course as well. So look into that if you're interested. Now let's move on to computer vision. After you've learned, the basics of Gen AI, how to do prompt engineering, data science, and machine learning, I think the next step is, specialization. So you need to learn computer vision or NLPLM. We have worked with a lot of students. Some of them are more interested in LLM application, but there are always students whose job is, asking for like computer vision and different types of use cases. So let's talk about computer vision specialization first, and then we'll move on to LLM. Computer vision, is not just image processing, right? So traditionally, we're going to use tools such as OpenCV to process image, and it has some sort of machine learning capability as well. But I think the modern computer vision problems are mostly solved using deep neural networks. But deep learning is just a foundational layer. You also need different types of computer vision architecture, such as convolutional neural network, and now the vision transformers. There are different, ways for you to sort of do feature representation, and then you apply that to different use cases. So image classification is one of these, simple use cases, and it's very similar to machine learning and Gen AI framework we just talked about. It expects the input and it gives you output, right? Whatever happens in a deep neural network, you can think of it as a black box. But if you work as a data scientist or AI engineer, I think you need to look under the hood and understand how that works. But as a user, or just to trying to understand how this works, you need to feed input into the deep neural network, right? And the deep neural network will try to learn the representation of these images. And here, the goal is to classify images into 2 different, types, either blueberry muffin or chihuahua, right? And the data will need to be labeled, which means we need to teach the deep neural network algorithm learn, about the differences, right, between chihuahua and blueberry muffin. So your data or the input that feed into the learning process need to be labeled, which means you need to tell the deep neural network that this is an image of blueberry muffin, the three images on the top, right? And three images at the bottom, they're Chihuahua images. So the deep neural network know that these are different images because they're labeled differently, and they will try to learn different representations. They're trying to understand the similarities and differences. And after the model has been trained, right, it sort of understands how to represent a dog image or a bluebird muffin image. It's some sort of automatic feature extraction tool. So when you feed a new image, right, this Chihuahua's image, the deep neural network, which is a trained model, it has learned from a lot of images, right? And it's able to sort of turn this into features, and then it will be able to run the classification model and that it will generate the prediction, which is a probability, right? Now, in this case, the probability of this image being Chihuahua is 95%, and that's why it will classify this image or label this image as a dog image instead of a blueberry muffin image, right? So that's essentially how it works, and we sort of skipped the exciting part, which is how this algorithm is learned or trained, right? But that's something you have to learn, in a course. You need to have the machine learning fundamental knowledge, know how to work with deep learning tools such as PyTorch, and then you need to learn how deep neural networks work. Okay. All right. As I said, I think the trick of doing deep learning for computer vision is all about image representation. So people have come up with many different types of architecture, deep neural network architecture, to represent, these images, right? There will be basic ones such as convolutional neural network, which is a family of algorithms and architecture, right? And it started from Google's LeNet, but there's also other, architectures such as ResNet and BGG. There are new, architecture being proposed on a weekly basis. And then these architecture will basically do feature extraction, as what we see here. An image is broken down and goes through different layers, and eventually, these are the representation of these images, and you can use that for, classification purpose. Okay. Computer vision has many different, applications. Right? You can use that for example, semantic search. It all depends on the use cases. In this case, it's I think it's a website for semantic search. I think it's for research purpose. So it has a huge libraries of images, and these images have already been sort of, indexed in the database. So each image is represented using some sort of feature, feature representation. And then when you upload a new image and say, find similar images for me, this is, and then it's going to calculate the similarity between one image or the image you upload with the entire library of images, and it will return you the similar images. So that's semantic search. And there's one interesting use case, for example. I've worked on a project before where the client, they have a huge catalog of furnitures, and they want their customers to sort of upload image of their existing furnitures or their bedrooms, or and it's going to basically recommend new furnitures based on images they uploaded, because it was trying to match like their style. Imagine you're moving from Toronto to New York City. You don't want to, pack everything and, rent a U-Haul and drive to New York City from Toronto. Maybe what you would like to do is you just work with this company, and you just upload images of your current, bedrooms or whatever, your furnitures, and it try to understand what you like, and it will find a catalog of, furnitures that you like. And then they will basically, find people to help you purchase everything. And when you fly to New York City, you can just move in directly, and you have everything, set up for you. There are actually businesses out there that does this. It was very interesting. And then they use machine learning and semantic search to help, pick furnitures for their client. Okay. But there's some other applications such as, semantic segmentation. And there's semantic segmentation, but there's also instant segmentation. This is really important in a lot of the research in medical imaging, healthcare, autonomous driving, lots of use cases. But again, the fundamental knowledge you need to have is, traditionally it's convolutional neural network, which is feature representation, and then you can apply that to different types of use cases. Okay. This is one of the architecture. I think that it's the GoogleNet, but that's how an image, right? Starting from the left, it's basically a two-dimensional array. We have x-axis and y-axis. In this case, it's 32 by 32 pixel image, and you convert that to NumPy array, or what we call tensors, and then go through the convolution layer and also pooling layer. When we say it's deep neural network, it's because it stacks many, many layers together. But some genius out there will come up with this kind of, architecture that has been proven to work really well in practice. And the open source community will basically, pick these architecture and then apply that to their specific use cases. So that's the CNN and also architecture. This is the traditional approach to do machine learning and computer vision. But I think in recent years, there are also other innovations, such as using transformer-based architecture. In a lot of the benchmarks, Vision Transformer has outperformed the traditional CNN, architecture. But recently, it's having some sort of comeback, and people are trying to combine both CNN and also Vision Transformers, which is very interesting ideas. But I think that's what you need to learn in computer vision. So these are the resources, or the things you need to learn if you would like to get specialized in computer vision. First of all, you need to understand machine learning and know how to do basic stuff like PyTorch and Hugging Face, right? Know how to build deep neural networks, or if you have a pre-trained model, how do you load that into Hugging Face and use that, right? And then you need to move on to the data preparation. Before you jump into AI and algorithms, it's always important to know how to process data. And traditionally, data has been, when we say data analysis, most of the time we're referring to structured data, like data, CSV data, right? JSON data or semi-structured data. But here, for computer vision, the data is image or videos, right? Could be graph data as well. So you need to know the basics of image processing. There are different libraries. OpenCV is still very popular, but it's not just cleaning and processing, pre-processing image. You need to know how to do data augmentation as well. This happened to be one of the most important topics in computer vision, because if you want to get good performance out of your models, the data is really important. And in real life, we know labeled high quality image data is always expensive to get, right? And it's garbage in, garbage out. If you have really good data and you have lots of them, and you have the computing power, you're going to get a very decent model. But what if you don't have enough data? People do, in practice, do data augmentation. There are many different ways to augment data. You can do the traditional things like, image shearing and, just transposing your image and things like that. But now we can use generative AI to do that. For example, the stable diffusion models, the GAN, VAE models, but these are just generative models that can help you generate synthetic data. And it's like changing your images slightly, or the augmentation is really just changing your image, right? Changing the orientation and stuff. You can flip the image, but synthetic data means you are going to use all of your input images, feed that into a generative model, and it's going to generate the synthetic data. And you can use that to augment the data, and then you'll have lots of data for training the downstream tasks. This is very, very powerful because when you get enough data, your model accuracies can usually get significantly boosted. Data annotation is also important. So you need to understand not only how to do that manually, but also how to leverage, let's say, human annotators, like working with Mechanical Turk service. But ideally, we automate that using using APIs. So you can work with Amazon SageMaker, Ground Truth services to do that. It requires a little bit coding for sure. Okay, so that's data processing, and then after you have the data prepared, you need to understand the basic, architecture, right? It's not just a deep neural network, but it's also the convolutional neural network, architecture. So you need to understand the basics, the architecture, different architectures, and then you can start to learn how different use cases, right? You can do object detection, image segmentation, instance segmentation. You can do depth estimation as well. We can analyze pose. So there are many different use cases. If you want to become a computer vision specialist, you need to understand at least three or four of these commonly used use cases, right? And definitely segmentation. And after that, I think you need to learn generative models, right? Vision transformers. There are a ton of them out there, but understanding the basics of generative models is very important. And then I think the next step, I didn't include that here, which is multimodal, which means the new Google Gemini model is not just a text model, right? It's multimodal because during the training phase, it feeds both images, text, and even video into the training process. So the model understands, images and text at the same time. And so multimodal modal models are becoming a very hot research area, and you're definitely going to see a lot of interesting and exciting applications. So that's computer vision. There's some resources. WeCloudData has a computer vision course, which is part of the AI engineering bootcamp. So you can choose to specialize in computer vision. But the best learning resources out there, Stanford has the CS131, CS231. These are really great courses. You can look into MIT's Deep Learning for AI and Computer Vision. I believe videos are on YouTube, and you should be able to just Google and find them. Okay, so that's computer vision. Now let's move on to large language modeling, which is NLP, text. And again, you'll see this, repeatedly. Deep learning, machine learning, Gen AI, they all expect input and gives the output, right? But the traditional ML deep learning models require a lot of labeled data for training or learning. And we know that collecting labels or annotating data is quite expensive, right? How do we label them? Well, we can do that manually, but then you cannot scale that if you do that yourself or within your team. That means your data is fairly small. If you want to train a very powerful, transformer-based model, you probably need a ton of images. We can use Mechanical Turks, which is human labeling service. There's also Label Box, right? Different, services out there. It's not cheap because they charge you based on, the unit of tasks, which means if you have more images, then you need to pay more, right? So you need to have proper funding in order to do that. But what if you're dealing with millions of images? Then the cost of labeling these data is simply too high, right? So how can we possibly label so much data, right? Like, do we always need to start from scratch and label all of these data? And for many companies, they wanted to do something like this, but then this is the biggest I think roadblock, right? They just simply don't have enough data. So I think the solution to this is maybe we don't label all of these data. There's something called self-supervised learning, which is the next token predictor we just explained, right? Self-supervised learning. Imagine how children or kids, right, learn or babies, I should say, baby learns how to walk, right? You don't have to show them many examples. They don't even like maybe at that time they don't even speak. They don't even like they don't read yet, right? So they mainly do learn things through vision, like different senses. If they're going to walk and a little bit fast and they couldn't hold on to something and they fall and it's painful, they cry and learn from that, right? But you don't put them in a classroom and say this is the proper way of walking and running. They can barely read, right? So self-supervised learning sort of just, is inspired by that, right? So let's say we have generated so much text on the internet, right, in the past 20 years, and we can scrape those data, and there's so many text, right? And we can basically use self-supervised learning to generate, labels, because if you want to predict the next word, which is usually how, that's how we speak. Like we speak word by word. When you work with ChatGPT, it also spits out the answers like word by word, right? It doesn't give you the whole paragraph at the same time. It actually types like one word at a time. So that's why when we have a corpus of text, right? Let's say you get the blog posts, you scrape from some website, you can start to construct your training data set automatically, right? So nothing is impossible. So you can have like nothing is, right? And your sentence is nothing is impossible, but you can use nothing is as the context or the input, and impossible is the output, right? Even follows by the followed by word, and even the is followed by word, right? So nothing is impossible. If you type in nothing is in ChatGPT, it might actually just predict impossible. And the reason why I know how to do this is because it's still a statistical based model. It has seen nothing is impossible on the web so many times, right? So in something called self-attention in the transformers, it knows that sort of after nothing is, it's more likely to be impossible. But there are other potential tokens. Nothing is working, but it's probably not as popular as nothing is impossible, right? That's essentially how it works. And that's why I think when it comes to pre-training a large language model, it's more about, do you have enough computing power and GPUs, right, to train your models on more text data? And that's why NVIDIA's stock price is so high right now. Everybody's begging them to ship GPUs to them, right? So that's the self-supervised learning in a nutshell. And based on this and the transformer architecture, people created a lot of foundational models, which are the models pre-trained on large amounts of data, and they either open source it or they keep it in-house. But for example, Meta open source Llama 2, but now I heard that Llama 3 is coming out very soon. Google has Palm, but they also have Gemini, right? Stable Diffusion. So all of these are foundational models that's pre-trained on lots of data. But the foundational model itself is not as smart. It can do something like completion, but it hallucinates a lot. It doesn't always follow instruction. Like when you talk to ChatGPT, you feel like it's very smart, right? But the original GPT model is not as smart as ChatGPT, because it's almost like you've sent this foundation model to school already, and then it learns specialized things. It has studied different majors. But LLM is like like middle school or elementary school. It learns the most fundamental stuff like math, English, right? History, and maybe something like that. But it doesn't mean that they can do the job. Like they if you give them like some sort of like data science related job, elementary school student, I think majority of them cannot do that because they're not trained, in those professions, right? So they don't have that kind of specialized skills, but they understand the basics of math. So you have to send them to school, right? Go to colleges and universities, and they start to major in different things, right? And that is fine-tuned models or instruction-tuned models. You tune these models to understand instructions, or when someone asks something that's inappropriate, they will tell you, okay, I don't know, I don't know the answer, for example, right? But that's not usually how a foundational model works. The foundation model, it will keep spitting out words, right? It just try to predict the next word. But after you've given it some sort of instruction, it's like some sort of further training, it becomes smarter, right? That's why originally when Google Gemini got released, I think it creates a lot of biased predictions, right? It generates like the Elon Musk image, like it's like black Elon Musk, right? And then in a few days, right, it was in news and people are sort of criticizing it, the model. And then later on, when you ask like the Gemini, and it refused to answer this kind of questions or refused to generate images if you ask similar questions. So some inspections, it's either fine-tuned again, right, to reject, like know what questions to avoid, or it's already built into the basic prompts. So whenever you ask this kind of questions, it will tell you that, I can't do it right now. So, but again, foundation model takes a lot of time and a lot of effort to train, right? It doesn't make sense for you to sort of, for everyone to do that, because the cost is simply too high, and we definitely don't have enough GPUs to do this. And that's why a few big companies will work on the foundation model. They open source that. And the industry and most of the people out there, they will be just using the existing foundation model or fine-tune models further for downstream tasks. Okay, this slide was prepared like 3-4 months ago, and it's already outdated because it's evolving so fast right now. There's so many new models coming out, but it's okay. Like I don't think the details matter, but it's just a timeline of large language models or some of the foundational models. Okay. I think I mentioned this a couple of times, the transformer model. It all comes from this, attention is all you need paper, published by Google, I think back in 2017. And it's nothing new, but it was I think the first time that we are able to solve sequence to sequence models in a more distributed fashion, which means you can train a model so much faster in parallel. And GPU is the perfect fit for that, and that's why these companies are able to train transformer models on really massive amounts of data, right? Terabyte and terabytes of text data, and that's why we got these powerful large language models. Okay, the detail probably doesn't matter, but this is the training data, LLM training data. Common Crawl is basically a snapshot of the internet. And it looks like the Llama 2 model by Meta, 67% of the training data is from basically data scraped from the web. Right? It's Common Crawl, but they have the C4 data. I think was prepared by Google. It has basic coding capability because 4.5% of the data is from GitHub, Wikipedia data, books data, right? Research papers, and Stack Overflow. And that's the training data. And sometimes just like trying to look at the training data used also tells you like, the specialties of a certain large language models. Okay. And I think OpenAI's models are more using the data scraped from the web directly, but while the Falcon model is using a different set of data set. So each one of these models have their own strengths and weaknesses. If you want to learn large language models, you need to understand the life cycle, right? How the different steps a raw model goes through, right, until it becomes useful. So we start from something that's more random, right? When we say we have 180 billion large language model. It means it has 180 billion parameters, right? In the deep neural network. When we train a classical machine learning models like using logistic regression, there are very few parameters. The reason why deep neural networks are so powerful is because you can stack up so many different layers of so many different layers that of neurons. That increased amount of parameters, right? And each neuron, there are some parameters to learn. And we have billions and billions of these neurons, and that's why the computation cost is so high. But before the model is trained, the parameters, like billions of them, are randomly assigned, or there's some sort of initialization, mechanism. It's too technical, but assuming that it's randomly, assigned, right? And as we feed these data points into the pre-training stage, which is the foundational model, pre-training, right? That's the autoregressive model we talked about, just predicting the next token. This is one of the most expensive model training steps. It needs to see terabytes and terabytes of data, billions of parameters, right? And it outputs, or we generate, a foundation model, which is unaligned. Unaligned model means the model, will basically say anything, okay? It can spit out biased stuff, okay? Or, can say things that are violent, okay? And because we haven't taught the model how to behave, how to say the right thing, or being politically correct, right? So that's the foundation model. And then after that, it actually needs to go through further training, right? We have some sort of alignment process, or also instruction tuning. We can use reinforcement learning, but there are also other techniques we can apply to learn even without the human label. So that is instruction tuning and also alignment. This step teaches your model how to speak properly, and how sometimes will tell you that it doesn't have the answer. It reduces the hallucination, but not all of them, right? But you have an aligned model, which is way better. It understands instruction, right? It can do Q&A now instead of just predicting the next word, which may not make sense, right? Because it can predict the next word. There might be like 100 different choices. And if you choose one next word, it completely changes, the output, right? Because the next word will lead to the next word again. And every single step, it's choosing based on the probability. So a slight change, in the parameter or the way you align the model can yield completely different output, right, in the conversation. But after the alignment, right, the model becomes a lot better. It understands your instruction. That's essentially how it works. And it's also called supervised, fine tuning sometimes. But after this, that's like basically GPT, 3.5, and you can use that to build chatbot and things like that. But a lot of companies, that's the Llama 2 model, basically, right? It's aligned, fine-tuned, and then we can use that to build downstream, models, or fine-tune models for downstream tasks. Let's say a bank would like to build a customer service bot using Llama 2, the large language models. They would like to build that in-house, right? But seems like you want the LLM or the Llama 2 model to understand finance, understand banking product, speak like a bank customer service representative. Of course, you have to send it to send it back to school and to learn something more about banking business, right? So that's like sending your kid to college to specialize in some major, right? That is the fine-tuning process. Fine-tuning typically will change or update the parameters as well. So it is still also a very expensive process, but there are more efficient way to do that, like parameter efficient fine-tuning. People find different ways to sort of reduce the size of the model, the parameters, and make it run more efficiently. But that's the fine-tuning process, which companies find very useful. So they're looking for data scientists and machine learning engineers who can specialize this and can help them to build in-house LLMs. right? That is more specialized in certain industry. That's fine tuning. There are also model merging techniques out there that allow you to sort of do some sort of ensembling. You have many different models, right? One model might be really good at one task, another model is good at other tasks. How do we merge these models? Or how do we do the distillation to have much smaller model? Even though we sacrifice, we know that when we reduce the model, we're reducing the number of parameters. And we can start with 200 billion parameters, but we can train smaller models, right? Tune a smaller model so it's much quicker and it's much less expensive to operate, because you want to put that into an application. You want the model to be used, at scale, and you want lower latency. So you can't really have very big models because the cost is just too high. So you want smaller models, but then you have to sacrifice some performance, right? So that's the teacher-student model, some sort of distillation process, which is also quite popular. But this is the typical process, right? An LLM go through. That's the life cycle. And most of us, when we talk with chat with ChatGPT, we're working with a line model, which is fine-tuned, right? That's instruction tuned already. It's really good at Q&A, but we can fine-tune models for other purposes as well. Okay, so that's LLMs. And when do we use each approach, right? When do we use aligned models? When do we use fine-tuned models? It all depends on the use case, what you would like to achieve. This is not an LLM course, so I'll skip this slide. There are lots of details here. Okay, I think I need to move a little bit faster. Okay, so pre-training. There are companies out there that they have the ambition to pre-train their own models, like Bloomberg. They pre-trained Bloomberg GPT for finance, right? So that model costs millions of dollars. But then if you can pre-train that on specialized data, proprietary data, then yeah, definitely going to get a very decent model, right? But it's quite expensive. And then fine-tuning models are definitely very popular. You can fine-tune the models to fit downstream tasks, but you can also try the indexing approach, which is building RAG. I think I'll briefly talk about RAG later in the application section. Okay, so how do we start with NLP and LLM? Again, you need to know the basics of deep learning and machine learning, and be familiar with different libraries such as PyTorch or maybe TensorFlow, Keras, but knowing the basics of scikit-learning is also very important. And then you move on to NLP. And here the NLP, I mean the traditional text processing and the NLP. So you need to know how to pre-process text, and data scraping and annotation. These are basically data collection, data preparation, very important if you want to build LLMs, because the text data is never perfect. It always need to be cleaned, need to be augmented, and need to be labeled as well. And whether you want to label the data all depends on the use case, but you need to understand the basics of natural language processing. And then move on to transformers, which is sequence models, right? I think understand the traditional methods such as like LSTM, long short-term memory models will still be very useful. But then since 2017, transformers architecture has become more popular. So I think understand the fundamentals of transformers is still necessary before you move on to LLM. Okay. When you learn large language modeling, you need to follow certain sequence, I think. You need to understand how to pre-process data or prepare data for LLM, right? And it's slightly different from preparing data for the basic text processing. You need to know how to augment data, text data. You need to understand different types of large language model, because this can be very confusing. There are encoder-only models such as BERT, right? Encoder, decoder only models and decoder only models. GPT models, ChatGPT, OpenAI models, right? The Falcon models, Gemini, all of these are decode-only models. It's really good at generative tasks, right? But if you want to use it for text classification, the encoder-only model is actually better. So the BERT, Roboter models might actually be a better option. So I think depending on what tasks you would like to apply LLMs for, you need to understand different types of LLM and when to use which method, right? So that's the large language model itself. But then I think the most practical one is how to fine-tune an existing model, right? There are different approaches like in-context learning, which is kind of similar to prompt engineering, indexing, right? And then, you need to work with like, vector databases and vector similarity search, and also, how to tune large language models efficiently using different methods. Okay, so that's the roadmap for learning large language models, and hopefully this is useful. In terms of learning resources, WeCloudData has the LLM course under the AI Engineering Bootcamp, but you can take this as an standalone course as well if you're interested. DeepLearning.ai, as I mentioned, it has a lot of great resources, and those are short courses. Stanford also has the CS324 and 224N course. Definitely look into that. It has a lot of details, and if you wanted the depth, I think these are really good courses. All right, so after you understand AI automation, the basics of Gen AI, and then learn machine learning and get specialized in LLM or computer vision, I think when you hit the job market, it's more about how do we solve this use case? How do we build applications that are actually useful, right? So I think you need to understand some of the practical use cases of LLMs. And here, I think, a lot of people have fear about, their jobs being replaced. No one can predict the future, but I think at this moment, right, Gen AI can replace a lot of the tasks. I don't think it's going to replace jobs yet, because I think most of the jobs are pretty complex, and companies try to standardize the process, but it cannot be completely standardized, right? So I think we need people who are orchestrators. Maybe some of these tasks can be automated using Gen AI or whatever AI tools, but we still need to understand how to put everything together. Because humans are really good at planning and reasoning, right? So I think this is something that LLMs are not really good at. And people say that, well, there are different schools of thought. Some people think that because LLMs are simply predicting the next word, it doesn't really understand what's going on here. It just has seen so much data, right? Statistically, it can always predict something that's really useful. However, it doesn't mean it really understands the image or it really understands the semantics and all of those. But there are also people who argue against that, right? But I'm more on the side of, I think LLMs are, they're just replacing some tasks. You can use it for automation. But the reasoning and planning capability is still not there. For example, Devon, it's the whatever AI software engineering tool, and it has significant improvement over like GPT-4 on certain computer science tasks. But when you look at the benchmark, right, it's correct 14% of the time. It's already like breaking records, because before that it was like 3% or something, which is the best. It was GPT-4 2.7 or something. So it boosted it to like 14%. So who knows, like 2 years, 5 years, 10 years later, whether it will get to 80-90%, right? But at least right now, I think its planning capability is not there. And there are a lot of tech giants or researchers believe that at least the transformer-based architecture is not going to be the final solution. I think to reach artificial AGI or artificial generative intelligence, I think we need a fundamentally different architecture. So something new that's mathematical needs to be created. So hopefully we get there, but I think people start to realize the limitations of LLMs. There's certain things it's really good at, but it's not good at everything, including things like reasoning and planning. Okay, but it doesn't mean we can't build things that make it smarter. So we always leverage these tools, but we still need to build other tools to make it better, which is something I will talk about related to agents. Okay. So we're talking about applications here. So I'll briefly talk about RAG, which is Retriever Augmented Generation. I think this is very popular right now. A lot of companies out there are trying to build RAG applications for lots of good reasons. Companies have concerns using ChatGPT, and some companies ban the usage of ChatGPT at work because they don't want employees uploading, right, companies or client or customers' data to the cloud. It is dangerous, right? Because you never know how OpenAI uses these data, whether they use it for training or not. They get into a lot of lawsuits, right? So if you want to reduce the hallucination of LLMs, make it more specialized, more knowledgeable, right? You need to feed the knowledge into, this knowledge engine, right? So where does the knowledge come from? If you want an LLM to be really good at finance, right, then there are two approaches. You send it back to school, right? Learn everything about finance, but that means you need to give a lot of finance-related data or text data or image data, right? And feed that into the pre-training process. So you train a new foundation model, just like the Bloomberg GPT. You can do something like that. But it's super expensive, and you have to retrain that all the time, right? Another way to do that is, can we leverage existing LLMs because they're really good at conversations, understanding things, and we can do prompt engineering. So it sort of can learn something, right? Learn things through prompt understanding. So why don't we build an external knowledge base, right? A database that has all the knowledge about your company's HR policy, finance, or whatever, like manufacturing, right? And then we leverage large language models to do the retrieval and generation, which means instead of retrieving everything from its world, like the LLM itself, because LLM, you can think of it as the compression of the whole world. Like whatever happens on the internet, you feed that into LLM, and it compressed that down to a model that has 180 billion parameters, right? But it definitely doesn't know the things that it have not seen, okay? But we have this finance database, right, that has all the finance knowledge. So we can always do something called retrieval first, which means there's some ways for us to index these knowledge in a database. And when someone asks a question about finance, it retrieves, certain knowledge first, right, from that big database, and then it feeds that into the large language model, as along with the context and whatever questions and prompts, and then ask the large language model to either summarize it, right, or generate some interesting insight. And that also allows the company to sort of not uploading their own data to the cloud, right? They can just work with an open source model, and then the proprietary data is stored in the database, right, the knowledge base, and you can just retrieve that during the question time, right? So that's how it works. So it needs a couple of things, right? Such as the knowledge retriever. You need a large language model that can do embeddings and generations, but you also need a knowledge base, right? First of all, you need all of your data to be indexed or stored in a knowledge base, and then you can retrieve that in a very, very efficient manner, right? So it's building some sort of index, right? Index all of your knowledge, and then these knowledge will basically be created as embeddings, or basically just vectors of numeric values. And we know in the vector space, right, these are just vectors, and you can calculate similarities. If they're closer together, right, then they're more similar. Okay, so all of these documents are indexed, and they have vector space like distance, right? So certain documents are related, similar to each other semantically. Okay, that's the first step. Your company's knowledge base, index that. And then someone will be asking questions, right, to this RAG application. Let's say the question is, who won the World Cup 2022? You sent that to a knowledge retriever, but the first thing it does is, well, it doesn't understand the question. So you have to use a large language model to generate the embedding. So it has some sort of semantic meaning, right? So you're going to send this to an LLM that does the embedding, but basically converts your question or context into a vector, right? And then it sends it to the knowledge base. It's sent, the Q here means question, right? The question embedding gets sent over to the knowledge base. And you're basically going to project or map that onto this vector space. So your question is somewhere here, and there are a bunch of documents that looks quite similar to it, right? What this database does is just allows you to search and find, similar documents very quickly, right? And in this case, it decides that, well, one of these documents are, very similar to the question you ask. And it could be some sort of, blog post or, news page, right? Argentina were crowned the champion, blah, blah. But it's not in pure text, right? It's actually in the embedding space. So it sends the embedding back. Now you retrieve the similar document, right? And that document is going to be sent back along with the question embedding. So you have the question, which is the context, and you have the document you retrieved. And then you send that to the large language model again. The LLM can generate some sort of answers, right? And it will sort of rephrase it and say, summarize it and say, Argentina won the 2022 World Cup in Qatar. So that's in a nutshell how it works. But to build an effective RAG application, I skipped a lot of details here. There are things like re-rankers, the way you chunk the documents. There are a lot of tips and tricks here in terms of how to build a very effective one. But the bar becomes lower because it's all open source. I think it's very easy to, quick to get started with, but building something that's very nice is going to take some effort and expertise. Okay, so that's RAG. And next, I would like to talk about AI agents. I'm no AI agent expert, but my understanding of agents, for example, when you work with tools like LangChain, right? LangChain is an AI agent tool. It allows you to build simple RAGs, but you can use it to load like large language models and build like Q&A build chatbot as well using LangChain, right? But you need to stitch a bunch of tools together, of course. But LangChain has this specific feature which is called like agents, right? The agent workflow works this way, but basically ChatGPT is not able to do everything for you, right? It excels at question and answering because it's fine-tuned model or a model fine-tuned on the GPT model, right? And then it performs certain tasks really well because it compressed the world knowledge and it can answer a lot of questions. But sometimes when you ask like questions about something that happened recently, if it's not in the knowledge of ChatGPT, then it will tell you that, well, my knowledge is up till January 2024. I don't know anything that happens after that. In the next release, they're going to give you more, like train the model on more data, then it will be more knowledgeable, right? But that's the limitation of for example, ChatGPT, and you can think of it as one agent. But sometimes what we would like to achieve, we need multiple agents to work together, right? There are agents that can do web scraping really well. There are agents that can comprehend things really well. There are agents that can automate certain tasks really well. So for more sophisticated tasks and workflow, we might actually need to leverage different agents, right? So the agent tools here, right, are a layer that allows us to sort of decide or automatically decide it has some sort of planning capability and say, well, to achieve this task, right, you need to break it down to 5 different tasks. And for each one of these five steps, right, you need to call certain agent or LLM models to perform that task. But ideally, it is able to sort of decide on its own what is the best agent to use or what is the best LLM to use for a specific task or for a specific step. So it has this sort of basic planning skills and leverage certain agents to perform certain tasks. And when you put them together in a workflow, it can achieve the goal. Right? So that's AI agents, and I strongly believe that AI agents is going to be the most important, most useful thing, because I think it gives generative AI planning capability, because without this, we can still hard code the rules and say, well, if the questions is like this, then we're going to use this, right? But the agent tools allow you to sort of, automatically choose the agent. That is, I think, very powerful idea. So that's AI agents, which is more application related. So if you come from software engineering background, you don't specialize in AI and deep learning, you can still work, build exciting, I think, applications using these agent tools, right? It's more on the AI development side. So I think that creates also new job opportunities. So if you would like to work in Gen AI, you can get specialized in data science, or I think data scientists all need to upskill themselves to learn Gen AI, right? And understand how to build RAG applications. But people coming from back-end and software background, they can learn how to work with AI agents to build, Gen AI powered applications. I think that's another area that will create a lot of jobs. I think a lot of companies are excited about this. Okay. One example is, for example, a SQL agent. This is, I think this is taken from a blog post. I think the company is Abacus AI. But basically, it's a simple agent application, right? Let's follow the steps here. I think so. It's trying to build an AI agent that can help you write SQL queries and do data analysis, right? Trust me, it's definitely not going to replace data analyst, but it can actually help data analysts become very efficient, right? I don't know how practical this can be in there are definitely props and challenges, but theoretically, it's a very interesting idea. So in your data warehouse or data lake, right, there are a lot of metadata about the data, like the database schemas, right, and all of those metadata information, and those are text data. And the metadata, you can feed that into a large language model to create the embedding, right? Similar to RAG, you can sort of embed these metadata and store that in a vector database. So you're building a retriever system, right? It's like all of my tables, data types, schema, their entity relations, somehow you're going to index and store that in a database, okay? And then when the user, which is a business analyst or data analyst, submit a query, but the query is not going to be writing a SQL query. He's going to use natural language prompt or even voice prompt and say, I want to analyze these two, I'd like to generate this report and I need these data. I would like to merge these tables, something like that, right? You can ask a business question, or even say that, who's the top performers on the sales team based on the sales metrics in the last 2 weeks, right? And it's going to basically send that to the AI agent. The AI agent will need to decide, okay, what do we do here? There's a question, and then it decide that, okay, we are going to send this query to the document retriever, which is the vector database. And first of all, it needs to parse or understand the question and figure out, okay, what tables do we need to deal with? Because I need to write some queries for you, but I need to understand which tables to work with, right? So it's going to talk to the retriever database and say, okay, if someone's asking about sales performance, then we probably need to deal with the sales tables, right? And it has some sort of conditions, but we'll leave that to the large language model, which is fine-tuned, right? that can perform this kind of tasks. And then it retrieves the relevant tables. Okay. And now this agent is going to think about it and say, okay, so now I have the query, like the question, and I also have the related tables. Now I need someone or some agent to help me write the query, to actually formulate the SQL query, right? Now talk to the LLM. The LLM can actually generate code, right? So basically it rewrites the query and also add the context information, which is the tables to work with, and it generates the query, right? And the agent is going to be able to submit the query to the database and get the results of the SQL query. And when it gets the query, it needs to send it to another large language model and summarize it and say, well, can you summarize the report and answer the question here? And that's how the whole thing works, right? And you're dealing with different LLMs or even the same LLM multiple times. But this agent tool is supposed to understand how to do that. Okay. But it's, I don't think it's that perfect yet. But it's definitely an interesting idea. So do we prevent this from happening, or do we just work with it and we become very efficient, using these agent tools, right? I think that's what we need to at least be prepared for. I think it may not turn out to be as smart as we think. It may take like still 10, 20 more years to get there. But along the way, I think we need to adapt to these trends and be very good at these tools. Like, because everybody can do prompt engineering. There's someone who's a little bit better. But imagine you're the person who know how to work with AI agents, fine-tune models, and build applications. Then you're still among the top 10% of those people, because majority of the people will still at the level of just using prompt engineering to ask basic questions, right? All right, so that's AI agents. So there are things like RAG you need to learn, right? So when you learn RAG, there are new tools you need to learn, like LangChain, Llama Index. The Llama Index is specializing, like, preparing data for RAG applications. You need to understand how to chunk the document. I have a friend who works, for a company that builds AI solutions for, like customer service, right? So they built customer service bot. Google is providing solution to them, and then the models they built in-house, or the RAG they built in-house, is way better than the solution provided by Google. I said, okay, why? How come? They are Google. But he said that, well, the trick is all in like how you chunk the data. They did some, tricks that converts all the PDF document, because when you deal with real life data in a PDF, you have images, you have tables. Those are nasty data, very hard to deal with. And because most of the time we think that, well, it's just a bunch of text, but they have structures as well. So how do you chunk those documents and store that in vector databases? That is actually a very important step, and they did very well in that, and that's why their approach is, outperforms Google's model, right? But yeah, so these are some of the things you need to learn. And then building AI agents, I think you need to be familiar with, again, some frameworks, right? There's some agent architecture you can study, such as profiling and things related to memory, not the computer memory, like actually having memories, right? Memorizing things, doing planning, actions. But yeah, just Google around. I think you'll find useful references. Okay. So that's AI applications. If you would like to learn how to do that, WeCloudData has a LLM engineering course. It's part of the AI engineering bootcamp. We also have something called LLM Ops, which is part of the MLOps course. So this is the course that covers, RAG, and also how to build basic agents. But it's not a very advanced level, because this field is still very, very new right now. Okay. But we do build some really interesting RAG applications in the course. Deep learning AI, the best way to learn is actually read LangChain and Llama Index documentation. They have a ton of use cases and tutorials. Look into that. There's some great Medium blog posts as well. Okay. All right. Lastly, I would like to move on to MLOps, because we've talked about like computer vision, large language modeling, but these are at the theory level, right? if you want to build applications and make them run in production, you need these models to run in production. Then we cannot skip operations. So model operations is very important. Typically data scientists think that, well, whatever code they write for training the machine learning model is the most important piece. But it turns out that that's a very small code base. Like in production system, ML code base is very small. And you need to spend significant amount of effort on data cleaning, data collection, right? Serving the model. So you need model serving in deployment infrastructure. You need to do monitoring because things can very much go wrong at any given time. So you have to monitor everything, resource management. So a lot of things you need to know if you want to put things into production. So that's MLOps, and it touches on DevOps as well. Okay. This is traditional MLOps. It's already very exciting and very overwhelming. I won't dive into details today. We can have a follow-up MLOps, engineering session. But the way we look at MLOps is that, well, you need to know a little bit data engineering, because if you want to automate everything and put things in production, you need to automate data pipelines. If the data is not cleaned and processed in an automated fashion, you can't build production systems. So you need data engineers, or at least the ML engineers need to understand data engineering. And after that, you need to do model engineering. This is where the data scientists spend most of the time on, right? Working with different frameworks to train and tune models. But when you put things in production, you also focus on, model packaging, right? All the model artifacts, where you store them, how do you structure the folders, right? Distributed model training, where you have lots of data, how do you version control your data, and things like that. So these are model engineering. And after that, we need to do software engineering, right? So ML engineers, I think a lot of ML engineers come from software development background and software engineering background, because you need to know how to serve models, which means building some sort of endpoints, and you need to know how to scale that, because your company might be going with like a microservice approach. So you have lots of models, and each model is like one API, right? And you have to deploy that. You can use Lambda, which is serverless, right? I think I think all the Mistral models people use out there, it's all served through Lambda functions. It's serverless, right? It's quick and easy to get started with, and makes sense in some scenarios. But you can have like very specific, infrastructure, such as Kubeflow running on Kubernetes or Seldom, or SageMaker from Amazon Web Services, but these are quite expensive. So you have to make decisions what makes sense or not. And then there's also unit testing, because when you deploy the models, you have to do CI/CD. So you have to write test cases as well, right? And after that, we have to deploy everything. So that is DevOps, right? But of course, DevOps in the context of machine learning. So you need to understand how machine learning infrastructure works. That means Docker, serverless. You need to understand GPUs, and then working with one of these clouds, okay? And then CI/CD pipelines, whether it's code deploy in AWS or GitHub Actions and Jenkins and all of these things. Monitoring, there are open source tools out there. Pick one of them. You can even use AWS to like manage the services for monitoring. But yeah, and automation, right? Apache Airflow to automate data pipelines. But there are step functions and some of those tools. And version control. You not only version control the code, but also version control the data, right? And also, where do you store all of these features in production? Are you going to do batch data processing prediction, or are you going to have some sort of real-time prediction needs? Then you need to deploy the models as API endpoints as well. So if you want to become MLOps engineer or ML engineer, I think you need to choose your specialization. If you know all of these, great. I think you're gonna get paid really, really well. But you can choose to focus on data, model, right? Or you can choose to focus on the MLOps, which is focusing more on like, DevOps. Yeah, so I think there's too much to learn here. Choose your specialization is useful, and you can always start from, let's say, data and model engineering, and then move on to model deployment, and then move on to infrastructure. Yeah, but if you want to learn all of these, just a plug here, we do have a machine learning engineering bootcamp that teaches all of these. And in the past, I think 2 years, another topic becomes very popular, which is LLM ops. How do you operate large language models in production? Again, we touched on some of these, like vector databases, LangChain, frameworks like this, right? And of course, you need to understand computer hardware. Interestingly, I think when we train the large language models, we know GPU very important. But if you look at NVIDIA's the report, you'll notice that actually majority of the money that goes to NVIDIA is not spent on training the large language model. It's actually spent on inference, which means if you want these language models to generate the next token, it also needs GPU instances or compute servers, right? And that cost is really high. I think the company behind Stable Diffusion called Stability AI, they're not doing very well. I think their CEO moved on. They had a new CEO. But they tried to open source this vast, like very popular large language model. The company is awesome, but they spent $100 million on something. They only generated 20 million revenue. That's the problem, right? And if you look at the bill, majority of them goes to GPU and NVIDIA because it's so expensive to serve these large language models. And that's why you need to understand optimization, or there's a new trend where people want to build smaller models and merge different models and even do tiny ML, which is deploying models onto edge devices. And Apple just released some. I think Apple is going to come out with something that like a local large language model without internet connection just runs on your iOS. I think that's going to change a lot of things, right? So compute, right? Distributed training, cloud infrastructure, model serving, and also how to build applications like RAG. LLM requires slightly different infrastructure. But again, this is going to be one of the hottest areas as well, because after most of the company have done some sort of, experimentation, they tried it out, they want to deploy that something like their MVP. Now we are talking about operations. It's not just model training anymore, right? All right, this is the landscape. Again, it's exciting, but it's also kind of scary. There's so many different vendors, different tools. There's quite a bit you need to learn. But the good thing is that like you don't need to learn 99% of these because, very similar services. You just need to pick a couple of core and popular ones, and that should be good enough. And which vendor your company go with, it really depends on like the company, and it shouldn't be very hard to adopt these tools because their main job is to make your life easier, so it shouldn't be hard. So I would go with open source, right? Go deploy a vector database yourself, know how to work with LangChain and Llama Index. These are very practical, but you don't have to learn like very specific like vendor tools because there's so many vendors popping out every day. All right. In terms of learning resources, we have WeCloudData has an MLOps engineering course. It's a 3-month course. We have self-paced version for flexible schedule, but we also have this as part of the machine learning engineering bootcamp. Highly recommend CS 329, which is ML system design course. Look into that. All right. I only have 3-4 slides left. I just want to quickly mention the learning options with WeCloudData. If you want to learn AI, Gen AI, and large language modeling, we have 3 options. We have self-paced course with mentorship. We have online live classes. That's like a traditional boot camp. We also have, AI projects. If you have the knowledge and, you've learned data science and machine learning already, if you just want to work on projects, we have real client projects as well. So I'm going to go through this again from a different perspective, just to, guide you through some sort of learning roadmap that we designed for the entire bootcamp. Okay. Again, the bootcamp has 3 courses, or actually 4: AI fundamentals, LLM, computer vision, and MLOps. I think first, before you jump into LLM and computer vision, you need to learn AI fundamentals. You need to make sure that you know Python programming, you know the basics of data wrangling, right? Machine learning and deep learning. By deep learning, I mean the basics of deep neural networks and working with PyTorch. These are just the fundamentals. We have an AI fundamental course that covers everything if you're just starting from scratch. Okay. And then I think you need to know some basics of cloud, because when you build like your portfolio project and stuff, you are not always going to do everything on your laptop, because your laptop might be Windows and it doesn't have a GPU card. So you need to know how to work with a GPU instance, either on Colab, or you can run that on EC2 instance in AWS. But the cloud, like which vendor, doesn't matter. It could be Azure, it could be GCP, right? I'm just using AWS as an example. And then you need to know like SageMaker, which is AWS ML framework, or I should say managed ML services, right? And then you go specialization, right? To learn LLM, you need to know, I think in this yellow box here is everything about data. If you want to get like a decent job, I think people care a lot about your data handling capability. Do you know how to do web scraping, collect data, annotate and label data, right? Do you know how to prepare data for instruction tuning or pre-training large language models? That's not the traditional data preparation stuff we learn, like, in a data science course, right? That's data preparation, augmentation for large language model application. And then pre-training large language model, instruction tuning, right? And then also after that, fine-tuning your models and building RAG applications. So I think this is what I would recommend as just as the learning path. Okay. For computer vision, again, you should start from data. How do you handle image data using the OpenCV? But there's Torch Vision, there's TIM. There are different libraries, right? Data collection, data preparation, image data augmentation. Also, how to use generative models to generate synthetic data is important. And then you still need to learn the basics of CNN, which is convolutional neural network, and different architecture, right? Definitely learn something about generative models and vision transformers, and then apply that, for object detection, segmentation, and different downstream tasks. Okay. And for MLOps, there's something called MLOps fundamentals. You need to know Linux, Docker, the basics of Git, right? Version control, and then how to use Flask and Fast API to build some simple APIs, because that's useful for model serving, right? A little bit backend knowledge will be helpful. If you come from software engineering background, that would be great. If not, I don't think these are hard to learn. So that's the fundamentals. And then you need to know infrastructure, whether it's serverless compute using Lambda, Kubernetes, right? And distributed model training using training and tuning using Ray, which is a new framework. There's Ray. You can use Apache Spark, but Ray is nowadays more popular, at least on the ML side, right? And then there's also always this data engineering element in MLOps, right? How do you automate data pipelines to generate feature? How do you store your feature, like in a feature store, right? So going from data to feature, and then you're going to do model training. In production, the training here is not really just training something in Google Colab or on your laptop in Jupyter Notebooks. We're talking about distributed training when you have lots of data. So it could be using Spark ML for distributed training, but you can use Ray for distributed training and tunings as well. Or LLM, computation distribution, whether it's data parallel, model parallel, or pipeline parallel, right? And then you need to understand how to do model packaging before you serve the model, right? And also set up the deployment pipeline, and then you have to monitor the models in production. So there's quite a bit to learn. But yeah, so we created this structure and keep improving the curriculum. It's definitely not perfect, but I think it's already one of the best curriculum you can get out there. So that's the learning roadmap we created. And again, we have 3 options. You can go with a self-paced program. The price will be lower, but it's not a Udemy course because it's a mentorship based, service. You can join anytime. And you do self-guided training. We have hundreds of hours of videos, a ton of like exercises and exercise solutions, or some of them are recorded as well. Content, and you work on 3 capstone projects. You basically work with a mentor on a weekly basis to complete projects. And we have Slack channel. Actually, we switched to Discord. And then we also have, apart from the weekly mentoring, there's also office hours where you can drop in if you have some questions. So we have weekly office hours for each program. So yeah, you actually get a lot of support. And the goal here is to complete the projects instead of just going through another course. So that's the self-paced option. We also have the actual boot camp. It's 6 months, 24 weeks, and the portfolio project building is included. Real client project is optional because it takes a lot of time. Some student will complete the boot camp first and then work on the real company projects to sort of bridge that experience gap. And we also have an additional 6 months of career mentorship. So it's like 12 months support, 6 months training, 6 months career and job search. Yeah, and in terms of the structure, I think you've seen that already. So we start from AI fundamentals, and then NLP, computer vision, MLOps, and then mentorship and real client projects. But if you're already very skilled, you graduated from like a data science program or some other machine learning engineering bootcamp, and if you struggle to get interviews and get jobs, maybe you just need that a few extra months of real experience to bridge that gap. So we have self-guided training, but it's not the self-paced bootcamp. It's training for a real client project. And then you get to work on 2 to 3 real industry projects. But the total duration is 6 months, which means if you just want to work on one project, it's doable. It's usually 2 months, a short project. So the fee will be lower. And the career mentorship is optional, so you can purchase that as a separate package. But yeah, that's everything we have. Hopefully the session is useful. You learn something new and also learn something about WeCloudData's offering.